Hi everyone and welcome to another special video. My name is Emmanuel Olega and I'm a math teacher and a software engineer. So today I'll be introducing a new topic or a new side. I'll call this the applications of differentiation. So we shall be learning about how to apply differentiation in rates of change. How does this work? All that in today's video. Right, so today we'll look at applications of differentiation. This is what we are on right now. So this video is good for someone who has already watched differentiation because now we're basically applying it in different situations. Alright, so let's begin on it. So applications of differentiation. So there are many applications of derivatives in pure mathematics, and here are a few examples. So one of them is rates of change in calculus, small changes in calculus, finding equation maximum and minimum value of a function, finding stationary points of a curve, Maclaurin's theorem, finding displacement, velocity and acceleration given as a function of time. So these are quite a few examples, but there are very many more, but these are a few and we shall be looking at some of these. Alright, so the first application we're going to be dealing with is the applications rates of change in calculus. Alright, so the rates of change can be expressed using differentials. So the fact is f prime x represents the rate of change of fx. So for example, the rate of change of a quantity p means the rate of change of p with respect to time. So this can be stated as dp dt. And then the rates of change in volume, area, height, etc. can be obtained by using chain rule. For example, if V denotes volume and H denotes the height of a certain shape, say a cuboid, the rate of change in volume of the cuboid will be denoted by dV dt. So by chain rule, dV dt shall be equal to dV dH times dH dt. Alright, so this is just quite of a few examples, but I'm going to try to explain as best as I can so that we actually understand what's going on. Alright, so let's look at an example. So in the first example, we're being told that a rectangle is twice as long as it is broad. Find the rate of change of the perimeter when the breadth of the rectangle is 1 meter and the area is changing at a rate of 8 centimeters squared per second. Alright, so first of all, one thing I always encourage for anyone doing these numbers is always draw a sketch of the problem. So, for example, we're being told that a rectangle is twice as long as it is broad. That means that the width or the breadth is twice. It means that the length is twice the breadth or width. So, we're going to let the breadth of the rectangle be x, and then when we sketch it, we shall have the breadth being x, and then we're going to have the length being 2x, and that's we've actually represented it. Then let's look at what has been given. We've been told that, if we look here, we've been told that the area is changing at a rate of 18 centimeters squared per second. So that means that the A dt is 18 centimeters squared per second. So in the question, we're also being told to find the rate of change of the perimeter. So that means we are looking for dp dt. And then we've been given x, which has been given in meters, but we're going to convert that to centimeters because of the units we see here, and then we can say that x is 100 centimeters. Alright, so now according to this question, you can see that what happens is we are connecting two different rates of change. We're connecting this rate of change here for area, and we're connecting that to the rate of change of perimeter. So when you have such a number and you want to find dp dt, I encourage you to actually first write the word dp dt. This will actually enable you to know what we are actually looking for. Then we're going to write an equal sign. Then what happens is we're going to have two different fractions on this other side with a multiplication sign. So first of all, you're going to first write down these letters that you see here. So we're going to write out the dp here over, then you're going to leave that blank, and then you're going to go here and you're going to write the dt. So this downer value here, you place it here, and then this upper value, you place it right there. Then the next question is, what we're asking ourselves is, so what, in this context of this question, what variables are we trying to connect together? So we're trying to connect this to area. So we're trying to connect the rate of change of perimeter to that of area. So that means that inside these two blank spaces, you're going to put the area. So you're going to put dA here and dA here also. So this is going to be the final chain rule at the end that will actually give us what we are actually looking for. So in the process, you just have to keep that in mind. Alright, so now that we've set that foundation, now we can actually now find the perimeter. So you can say that perimeter is going to be equal to 2 times length plus width. So which is the same as 2 into bracket 2x plus x. And then p shall actually be equal to 2 times 3x, of which p shall actually be equal to 6x. So when I actually differentiate this, I can get dp dx as being equal to 6. Alright, so now we have what dp dx is. So now let's go and find area. So area is equal to length times width. So we'll have it as 2x times x, of which area shall actually be equal to 2x squared. So now dA dx, if we differentiate that, we shall have dA dx as being equal to 4x. Now we also need to remember that in case you have an x remaining in any of these, you actually have to substitute in the value that you actually have here, because we need to know that x is 100 centimeters. So that means that dA dx shall actually be equal to 4 times 100, of which dA dx shall actually be equal to 400. Alright, so now that we found dA dx and dp dx, the next step is we need to find what this dp dA is. And now we're going to find dp dx, dp dA here, and we're going to relate it to the values that we actually have right here. So by chain rule, dp dA shall actually be equal to, so this is also how you arrange it. So you're going to have dp at the top, and then you're going to have this dA at the bottom right here. So now for the first case, because what the variable that has been given of what we solved right here in this context, it has to be x at first, because we are dealing with x at the beginning. So we're going to have dx here and dx right there. So when you do that, we're going to have dp dA being equal to that. So now we're going to substitute in the values that we've actually found. So now we found dp dx as being equal to 6, and then what we have in the question is dA dx, and that means that we just have, that means that dx dA is actually this, but with 1 over it. So it's just going to be 1 over 400. So we're going to find that dp dA is equal to 6 over 400, of which that is the same as 3 over 200. So now that we know that, we can now find the rate of change in perimeter. And that is because we already know what dA dt is, because it was actually given in the question. So now we're going to plug in this formula. So therefore, to find rate of change in perimeter, by chain rule, dp dt shall actually be equal to dp dA times dA dt. So this is what we're going to have right there. So plug those values in. So dp dA is 3 over 200 times dA dt, which was 18. So multiply those and we'll have 54 over 200, which is equal to 0.27 centimeters per second. And that is the rate of change in perimeter with respect to change in area. That's the answer that we're looking for. Alright, so moving to question number 2, we're being told that the side of a square is increasing at a rate of 4 centimeters per second. At what rate is the area increasing when the side is 8 centimeters long? So what are we looking for? We're trying to relate the increase in size of the sides of a square with that of area. But let's first sketch this. So when you sketch this, remember we're dealing with a square. So we're going to let the sides of the square be x. So that means that all the sides are actually going to be equal to x. Alright, so when we look at this question, we've already been told that the sides of the square sheet are increasing at a rate of 4 centimeters per minute. So that means that we have the x dt as being equal to 4 centimeters per minute. And then what we need to find is the a dt, and we've been also told that x shall actually be equal to 8 centimeters. So now in this case, we're trying to relate or connect the rates of change of area with that of the side. So we're looking for the a dt. So this one is direct. So we're going to be looking for the a dt. Now as I've said, first place the dA here times, then you're going to have the dt down here, and you ask yourself, what are we trying to connect it to? We're trying to connect it to this, the change in or increase in the sides of the square. So we're going to have dx here and dx also right here. So this is what we're looking for. Alright, so now let's first work this out. Now if we were to find the area, you can say that area is side times side, of which we'll have it as x times x. And then we have area being equal to x squared. So therefore the a dx shall actually be equal to 2x. But remember that x is 8 centimeters. So therefore the a dx shall actually be equal to 16. As you can see, we've already now found the dA dx. So we actually have one of the values already. And then in the question you're already given the dx dt, so that means that we've actually found all that we need to find the rate in change in area. So rate of change in area shall actually be equal to this. So by chain rule, we'll have dA dt being equal to dA dx times dx dt, just as we have it here. So we're going to have it as 16 times this 4. And then dA dt shall actually be equal to 64 centimeters squared per minute. Remember that since this is area, we're going to have this as centimeters squared, then per minute. And that is the answer we're looking for. Alright, so question number 3. We're being told that an edge of a variable cube is increasing at the rate of 3 centimeters per second. How fast is the volume of the cube increasing when the edge is 10 centimeters long? Alright, let's first label this and let's draw it. So we're going to let the edge of the variable cube be x. So we're going to sketch it. So this is the cube. Remember, in a cube, all edges are equal. So we're going to have x all around, as we have right there. Then we've already been told that dx dt, which is the rate in change of the edges, is 3 centimeters per second. And then what we're being asked for to look for is dv dt. But we also know that x is 10 centimeters, as we've been given right there. So that means that since we're looking for dv dt, let's see what we're looking for. So we're trying to connect rate in change of volume with that rate in change of the edges of the variable cube, because the cube is actually increasing in size per second. So now we have dv right here times, then we have dt down here. So this here and this here over. So what else we're looking for? We're looking for dx, because now we're connecting the variable x with volume. So we have dx right here. So as you can already see, we already know what dx dt is, so we have this already. So the only one we need to look for is dv dx. So good enough, we can find that through volume. So in that, volume of a cube is going to be equal to side times side times side, of which we'll have it as x times x times x. So v shall actually be equal to x cubed. Then dv dx, if we differentiate that, we'll have it as 3x squared. And then we know that x has been given as 10 centimeters, so we're going to plug that in, and then our answer shall be equal to 300, as we can see right there. So now we know what dv dx is. So now that we know that, we actually have all the requirements we need to find the rate in change of volume when that edge is increasing in size. So therefore, rate in of change in volume is this. So we're going to find it from by this chain rule. Dv dt should actually be equal to this dv dx times dx dt. So plug in the values, and we have dv dt being equal to 300 times 3, which is equal to 900. But remember that volume is measured at centimeters cubed or cubic centimeters. So we're going to have that as cubic centimeters per second, because the rate of change is measured per second. And that is the answer that we're looking for. Alright, so next we're being told that the volume of a cube is increasing at a rate of 2 centimeters cubed per second. Find the rate of change of the side of the base when the length is 3 centimeters. So that means we're going to draw the cube also. Now we're going to let the sides of the cube be x. And we've now been told that the rate of change in volume is increasing at 2 cubic centimeters per second. So we have dv dt already given. Then we're being told to find the rate of change of the side of the base when the length is 3 centimeters. So that means we're looking for the x dt. But then we've also been told that x is 3 centimeters. So now in this question, we're looking for the x dt. That means we're going to have it being equal to, so we're going to first write the x here times the dt here. And then right here, we're going to ask ourselves, what else are we comparing it to? Because we're being told that the volume of the cube is increasing at the rate of that. So that means we're comparing it to volume. That means it's going to be dx dv, and this shall also be dv, as you can see right there. Alright, so volume of a cube, we know it shall be equal to side times side times side, of which we shall have it as x cubed. Now when you differentiate this, we shall have dv dx as actually being equal to 3x squared. Then remember that x is 3 centimeters, so we're going to plug that in, and we're going to have 3 times 3 squared, which shall actually be equal to 27. So now that we have this, we found the dv dx. Now you can actually see that dx dv is simply dv dx in inverse form. So we're just going to inverse that times dv dt, which we already know right there. So now we can actually find the rate of change of the side of the base. So therefore, the rate of change of the side by chain rule shall be dx dt being equal to dx dv times dv dt, just as we had calculated before. So now we're going to plug in the values. Now dx dv is simply this in reverse or in inverse form, because this is dv dx, so we shall have it as 1 over 27 times dv dt, which is already known, and it's equal to 2. So multiply those and we'll have dx dt as being equal to 2 over 27 centimeters per second, and that is the rate of change of the base when the length is 3 centimeters. That is the answer they wanted. Alright, so next question, we're being told to find the rate of change of the area of a circle with respect to its radius when the radius is 6 centimeters. So let's first sketch this. Now we can let the radius of the circle be r, then we can sketch this, and there is the radius. So now we are being told to find the dA dt, but we've also been told that radius is 6 centimeters. Alright, so this question is different from the rest in that we don't know what the rate of change in radius is. So we don't know what dr dt is equal to. So we don't know that, but we're being told to find the rate of change of the area. But we've also not been told the rate of the change of the area. So we also don't know what the dA dt is, which is actually what we're supposed to be looking for. Now what we're going to do is, in this case, we're actually just relating them. So now the best thing that's going to happen is, since we don't know what the rate of change of the area is, that means all we're going to be looking for is, for something, we're just going to be looking for a formula that just connects the two rates of change. So we should just be looking for dA dr. So this is a unique case. So that means that the rate of change of the area of a circle with respect to its radius is simply saying we want dA dr when the radius is 6 centimeters. So now let's look at the area of this circle. So the area is pi r squared, of which dA dr shall be equal to 2 pi r. But remember that r is 6 centimeters, so we're going to plug that in. So I have 2 pi times 6, of which we'll have dA dr being equal to 12 pi centimeters squared. So that will be the answer that we're looking for this question. Alright, so now next let's move to question number 6. So we're being told that a curve has the equation y is equal to 8 over 2x minus 1. Then be told that given that y is increasing at a rate of 0.2 units per second and x is equal to negative 0.5, find the corresponding rate of change of x. So that means we are looking for dx dt. So let's first create the chain rule formula for it. So as you can see, this top value is what we're going to have right here, times, then the downer value here is going to be this dt. And we're going to have this as over. So what are we comparing to? So we can see we've been told that y is increasing at a rate of 0.2 units per second. So that means we're actually relating it to the rate of change of y. So we're going to have down here, we're going to have dy. Then here we're also going to have dy. So because that's what we're comparing. So now let's solve this out. So now we've been told that dy dt is 0.2 units per second. Then we're looking for dx dt. And then x has been said to be negative 0.5 units. So now we've been told that y is equal to 8 over 2x minus 1. So first of all, let's first differentiate this. So we can do that by using the quotient rule. So we're going to let u to be equal to 8, and we're going to let v to be equal to 2x minus 1. Now du dx shall actually be equal to 0, and then dv dx shall actually be equal to 2. So substitute these into the quotient rule formula and we'll have it this way. As you can see, these values on this side shall actually give me a 0. I mean, these values here will give me a 0, and I'll be left with negative 8 times 2, which shall be negative 16 over bracket 2x minus 1 squared. But we've been told that x is equal to negative 0.5. So we're going to substitute that in, and this is what we'll have. So 2 times negative 0.5 will give me negative 1, and then I have negative 1 minus negative 1, which is negative 2 squared, which is going to be equal to 4. So I have negative 16 over positive 4, of which the answer shall be equal to negative 4. So I now know the value of dy dx. So now that I know dy dx, I can actually say that dy dx is simply this in inverse. So this is dx dy, but it's actually the same. So this is now basically going to be equal to 1 over negative 4, and then I already know what the dy dt value is right here. So therefore, from chain rule, dx dt shall be equal to dx dy times dy dt. So plug those values in and I'll have dx dt being equal to negative a quarter times 0.2, of which dx dt shall be equal to that, and the answer shall be negative 0.05 units per second. So now when you get a negative answer, as you can see here, it simply means that the value that x is actually decreasing at that rate. So that's all it means. So it's okay to have a negative answer because it just represents a decrease. Alright, so let's move on to the next question. So this is question 7. So being told that a curve has the equation y is equal to 2x over x squared plus 9. Then be told that given that x is increasing at a rate of 2 units per second, find the rate of change of increase, find the rate of increase of y when x is 1. So that means we're looking for dy dt. Now let's write its chain rule formula. So that means we'll have dy at the top here over times, and then this dt will be down here. Now, since we're comparing it to the rate of increase of x, which is what we've been given here, we're going to write dx here and dx right there. So we're looking for dy dx, and then we know that dx dt has already been given. So we can say that dx dt shall be 2 units per second, and then dy dt is what we're looking for. So all we need to find is the value of dy dx, and then x is 1 unit. So from y is equal to that, we're going to first solve this to find its dy dx by differentiating it, and then we're going to use quotient rule. So we can let u to be equal to 2x, and we're going to let v to be equal to x squared plus 9. So we can say that du dx shall actually be equal to 2, and then dv dx shall actually be equal to 2x. So from quotient rule, this is the formula that we shall actually have. So we're going to plug in the values, and this is what we'll have right now. As you can see, this negative 2x times this 2x will give me negative 4x squared. Then we're going to have these 2 multiplying the values inside, and we'll have 2x squared plus 18. Now this and this subtract, and we'll have negative 2x squared. So that's why we have 18 minus 2x squared, as you can see right there. But we've been told that x is 1. So we're going to substitute the value of 1 where we have x values. And then we shall have a 1 here and a 1 right there. So as you can see, 1 squared shall actually be equal to 1, of which we have 1 plus 9, which is 10, so I have 20 squared down. Then here, 2 times 1 squared is actually 2, so 18 minus 2 is 16, so I have 16 over 10 squared, which is the same as 16 over 100, which is equal to 0.16. So now I know the value of dy dx. It was all I needed to find the dy dt, because I already know what dx dt is. So therefore, by chain rule, dy dt, as we've stated before, is going to be equal to dy dx times dx dt. So plug in the values, and you have 0.16 times 2, which is equal to 0.32 units per second. And that is the answer they wanted. Alright, so question 8, we're being told that a curve has the equation y is equal to 2x plus 4 over x minus 2. We're being told that a point xy moves along the curve in such a way that the x coordinates of the point is increasing at a constant rate of 0.05 units per second. Find the corresponding rate of change of the y coordinate of the instant that y is equal to 6. So that's what we're looking for. So that means we're looking for dy dt. But we've been told that dx dt is equal to 0.05. But let's first form the chain rule. So now we're going to have the chain rule formula is dy at the top over times, then we're going to have this, and we're going to have the dt down. And since we're connecting this to rate in change of x, so we'll have dx here and dx right there. So let's look at what has been given. dx dt shall be 0.05 units per second, and what we're looking for is dy dt, and y is equal to 6 units. So now we've been given that y is equal to 2x plus 4 over x minus 2. But before we even think of differentiating it, we've been told that already that y is equal to 6. So that means you can just plug it right here. So we're going to have y being equal to 6, so it will be 6 being equal to that. So when you cross multiply, I have 6x minus 12. When I multiply the 6 into this, being equal to 2x plus 4. So now I just need to collect like terms. I have 6x minus 2x being equal to 12 plus 4, which is 4x being equal to 16, of which x shall actually now be equal to 4. So now I know the value of x. So now that is going to be very useful. Now we're going to be making use of this value of x onwards. So now I can bring this equation back, and now I can solve it again to find the dy dx. So I'm going to let u be equal to 2x plus 4, and I'm going to let v be equal to x minus 2. And then I'm going to find that du dx should actually be equal to 2, and dv dx should actually be equal to 1. So from quotient rule, I'm going to have dy dx being equal to v du dx minus u dv dx over v squared. So when I plug in the values, this is what I have. So multiply this 2 in, and I'll have 2x minus 4 minus this one multiplies this, and they just stay as they are. But now remember that this negative shall affect the values in brackets. Then I'll have 2x minus 4 minus 2x minus 4. So now I can see that this 2x has cancelled, and I'll be left with negative 4 minus negative 4, which is negative 8. But remember, we found that x is 4, just as we've solved right up there. Then I plug that in, I'll have negative 8 over 4 minus 2 squared, of which I'll have dy dx being equal to negative 8 over 2 squared, which shall be dy dx being equal to negative 8 over 4, which is negative 2. So now I know that the value of dy dx is negative 2. So now that I know the value of dy dx, I can now plug this into my chain rule, which is dy dt being equal to dy dx times dx dt. So plug those values in. We found the dy dx as negative 2, and in the question we are told that dx dt was 0.05. So multiply those together, and I'll have dy dt being equal to negative 0.1 units per second, and that is the answer. Alright, so let's look at question number 9. So being told that a spherical bubble is decreasing at a volume of 4 cubic centimeters per second, and then we're being told to find the rate at which the surface area is diminishing when the radius is 6 centimeters. So this is actually a unique question. So as you can see, since the volume is decreasing, it means that we can see that dv dt is actually equal to negative 4 cubic centimeters per second. So that means it's a negative because it's decreasing. So I'm being told to find the rate at which the surface area is diminishing when the radius is 6 centimeters. Alright, so this question is unique because in this case we have to first see how volume and surface area all depend on the radius of the sphere. So first of all, in this question, the first step we're going to do is we're going to first solve for dv dt, and we're going to relate that to radius. So first of all, we're going to first relate that to radius, then we're going to find it as dv dr times dr dt. So first of all, we're going to see how this relates to radius. And why is that? We introduce this dr dt because the radius is changing as the bubble shrinks, or as the bubble decreases in size, as you can see right there. So that's going to be very, very important. So now once you find the dr dt, then you're going to use that to relate the two. Now I want to relate the rate of change of volume to the rate of change of radius, and that's what we've done right here. So once we have the rate of change in radius, which is this dr dt, because in this case dv dt is known and we shall find dv dr as we're working it out, we can now use this dr dt to find the rate of change of surface area, which shall be this. So we're also going to relate the rate of change of surface area to the radius. So this shall be dA over dr also times dr dt. Now in this case, from the working, we shall be able to find dA dr, and then dr dt we shall find from right here. So that's how we're going to solve this question. So it's actually a unique one where we have to compare volume and surface area. So first of all, we're going to let the radius of the spherical bubble be r. So that means that, as we've seen here, dv dt is negative 4 cubic centimeters per second. Then dA dt is what we're looking for. And then we've been told that r is 6 centimeters. So first of all, the surface area of a sphere, the formula is a is equal to 4 pi r squared. So dA dr should actually be equal to 8 pi r. But we know that r is 6 centimeters, so that means that dA dr should be equal to 8 pi times 6, which is 48 pi. So now that is dA dr. So now we know that. Now next, let's solve for volume of the sphere. So volume of the sphere is equal to 4/3 pi r cubed. So we're going to have dv dr being equal to that when we differentiate, so it shall be equal to 4 pi r squared. And then remember that r is 6 centimeters, so we'll have dv dr being equal to 4 pi times 6 squared, which is 144 pi. So now that we know dv dr and we know what dA dr is, we can now first solve and find the rate of change of radius. So we're going to plug in into this formula. So let's plug it in. So rate of change of volume, we know by chain rule it shall be equal to dv dt being equal to, because we're relating it to the radius, we shall have it as dv dr times dr dt. So plug that in. So we know dv dt is -4 and we found dv dr as 144 pi. So we're going to make dr dt the subject, so it shall be equal to this -4 divided by 144 pi, and that is going to be the value of dr dt, which when reduced it shall be -1/36 pi. So now that we know the dr dt, we can now find the rate of change in surface area. So by chain rule also dA dt also relating with area, relating with radius, because radius affects it, we shall have dA dt being equal to dA dr times dr dt. So now remember dA dr was 488 pi times dr dt, which we found here as -1/36 pi. So multiply those together and you can see we'll have it this way. So you can set the pi values cancel. So when we reduce this completely, we'll have it as -4/3 centimeters squared per second. Now because it's area, that's why we have it as centimeters squared, and that shall be the answer that we're looking for. Alright, so the next one is different. So being told that a spherical balloon is inflated such that the rate at which its radius is increasing is 0.5 centimeters per second. So being told to find the rate at which part A, the volume is increasing at the instant when r is 5 centimeters. And then part 2, the surface area is increasing when r is 8.5 centimeters. So actually this is more like the former question. So first of all, we're going to see that we've been given that the dr dt being equal to 0.5 centimeters per second. So now, first of all, we've been told to find the volume, the rate of change of volume in comparison to that. Now we already know that dv dt, now relating it to this radius, it's definitely going to be equal to dv. So first place v, dv over times, then we have the dt down. Because we're relating it to area, so radius, this shall be dr and this shall be dr. So this is basically obvious. So volume of the sphere is 4/3 pi r cubed. So we're going to find it as dv dr being equal to 4 pi r squared. Then when we substitute in this 5 centimeters here, we're going to have it as 4 pi times 5 squared, which shall give me 100 pi. So now from the chain rule, rate of change in volume, I'm actually going to make use of this formula right now. So now plug in the values that you have, and this is what I'll have. We know that dr dt is 0.5 centimeters per second, so multiply those together and I'll have 50 pi centimeters cubed per second. And why do I have centimeters cubed or cubic centimeters? It's because it's rate of change of volume. Alright, so the next part is to find the rate at which the surface area is increasing when r is 8.5 centimeters. So now we already know what the dr dt is, so that's okay. So we can actually relate that. So now the surface area of a sphere is going to be equal to 4 pi r squared. Then the ADR shall be 8 pi r, which we know that r is 8.5 centimeters. So when I plug that in, I'll have 68 pi. Now to find the rate of change in surface area, I know that now it shall be the dt being equal to the ADR times the r dt. So I'll have the dt being equal to 68 pi times 0.5, which shall give me 34 pi centimeters squared per second, and that is the answer. Alright, so next one, question 11. So I'm being told that a hollow right circular cone of height 18 centimeters and radius 12 centimeters is held beneath a tap that is leaking at a rate of 2 cubic centimeters per second. So that's the rate of volume. And then we're being told to find the rate of rise of the water levels when the depth is 6 centimeters. Alright, so first of all in this question, we're going to let the height of the cone be capital H. We're going to let the depth of the water level be H. Then we're going to let the radius of the cone be R, capital R. Then let's let the radius of the water be R. So basically this is what we're looking at. So we've been given that dv dt, which is the rate at which the water is leaking, so that's like rate of change in volume, shall be equal to 2 cubic centimeters per second. So I'm being told to find the rate of rise of the water level. So that means if the depth of the water or the height of the water is small h, we're going to be looking for dh dt. So that's what we're looking for. So we've been told that leave the answer in terms of pi, and we've been told that find the rate of rise of water when the depth is 6 centimeters. So that means we want to do it when h is 6 centimeters. Now let's first sketch this. So this is now our cone here, and it is being filled with water. So now we're going to label it. So now we can see that the radius of the cone is 12 centimeters as given, and then the radius of the water, we're going to label that as small r, as we've stated right there. Then we can see that the height of the cone is 18 centimeters. That was given to us. And then we're going to have the height of the water, and we're going to label that as h. And that keeps changing, but depending on what value of h we have at a certain moment, we shall just substitute that in. Alright, now we need to find a way of actually finding r. But now there is actually going to be an easy way. As you can see, this is actually in rectangle form, and then this here is also a small rectangle. So you can actually find the value of r by actually using the knowledge of similar triangles to find that radius of r. So we know that from the knowledge of similar triangles, we can have this r over its height, this small radius over its height, and then being equal to this radius here over the height 18. So that is a law that in math that is actually true. So we have r over h, small h, is being equal to this 12 over 18. And then we can say that when this reduces, we'll have 2 over 3. So if we make r the subject, r shall actually be equal to 2 over 3 h. So now we know what r is in terms of h. So next, we're going to look for volume of the water. Now we know that v is a third pi r squared h. Now when we substitute that in, we're going to substitute in for r. So where there is the value of r that we actually found, we're actually going to plug it in. So I had found r being equal to 2 over 3 h. So we're going to plug that in here, and then we're going to square it. So when we square the values inside, we'll have 4 over 9 h squared. And then we can actually multiply this h inside, and we'll have it as h cubed. And then I'll have v is equal to 4 over 27 pi h cubed. So remember, in this question, we are looking for a relationship between v and height of water level. So that means we know that it means that dv dt should actually be equal to, let's first write the dv, then we're looking for dt, then we're saying that there is a relationship between it and water level. So here we're going to have dh, and here we're also going to have dh, because we're actually relating the two. So now from here, I can find dv dh as being equal to 4 over 9 pi h squared. So now I know what the dv dh is. Now what we're looking for is actually dh dt, but we already know what dv dt is because it was given to us in the question. So now here we've been told that but h is 6 centimeters because we've already been given the value of h. So dv dh should actually be equal to 4 over 9 pi times 6 squared, which I'll have it as this, which shall give me dv dh being equal to 4 pi times 4, which is 16 pi. So that is the value of dv dh. So now I can find the rate of change of the water level from this formula. So this formula says by chain rule dv dt is equal to dv dh times dh dt. So we already know what dv dt is, and we know what dv dh is from right here. So we're going to plug those in, and then we're going to make dh dt the subject. So making dh dt the subject, we shall have it as 2 over 16 pi, of which I have it as 1 over 8 pi centimeters per second. So therefore, the rate of rise of water level is 1 over 8 pi centimeters per second. Alright, so question 12, we're being told that an inverted cone with vertical angle of 60 degrees is collecting water leaking from a tap at a rate of 2 centimeters cubed per second. If the height of the water collected is 10 centimeters, find the rate at which the depth is increasing at that instant. So the unique thing about this question is we've been told that the cone has a vertical angle of 60 degrees. So that is going to be the key part. So as with the other number, we're going to let the height of the cone be h, capital H, and then we're going to let the depth of the water level be small h. Let the radius of the cone be capital R. Let the radius of the water be small r. So you can see we've been given that the rate of change or volume shall actually be dv dt being equal to 2 centimeters cubed per second. So again, we're also looking for dh dt because we're looking for the height at which the depth is increasing at that instant. and then we've been told that h is 10 centimeters. So let's sketch the cone. So this is what we have right now. So we have capital R to represent the radius of the cone, small r to represent the radius of the water at that moment or that instant. And then most importantly, we've been told that the vertical angle of the inverted cone is 60 degrees. So what that means is that the entirely from here to here we shall have 60 degrees, but if we divide this in half, it means that one half is 30 and the other half is 30. So that's what it simply means when we say vertical angle of the cone is 60 degrees. Now putting in the height, so the height of the cone is capital H, and then we've been given the height of the water level, so we're going to assume it to be 10 at some point. So to find the value of small r, we're going to use the knowledge of trigonometry. So we can see that we have this angle here, this is its opposite r here, and then we can actually see that its height here, which is its adjacent, is going to be small h, which is this height right here. So we can have tan 30 being equals to r over small h, of which if we make r the subject, r shall be h tan 30. But we know tan 30 is 1 over root of 3. So I have r being equal to h over root of 3. So now that I know the value of r, I can now find the volume of water. So volume of water, V shall be equal to a third pi r squared h. So now with this r, we're going to substitute with what we've actually found, which is h over root of 3. So square those values and we'll have h squared over 3. Then multiply this h inside and I'll have h cubed right there. So now multiply every term and I'll have h cubed over 9 pi. So if I differentiate this, I'll have it as, differentiating this with respect to h, I'll have h squared over 3 pi. But remember that h is 10, so we're going to plug that in and I have 10 squared over 3, which is equal to 100 over 3 pi. So that shall be my value of dv dh. So now that I know dv dh, I can now find the rate of change of the water level. So I shall make use again of the formula by chain rule, dv dt being equal to dv dh times dh dt. So there is a relationship between volume and the change in depth or height. So now plug this in and this is what I have. So dv dt was given as 2 cubic centimeters per second, and then I found dv dh as that. So plug that in, make dh dt the subject, it will be 6 over 100 pi, and then it will be 3 over 50 pi centimeters per second. So therefore the rate of increase of water level is 3 over 50 pi centimeters per second, and that is the answer. Alright, so the next question, we're being told that an upturned cone with semi-vertical angle 45 degrees is being filled with water at a constant rate of 30 cubic centimeters per second. If the depth of water is 60 centimeters, find the part 1, rate at which the depth of the water is increasing, part 2, rate at which the radius of the water is increasing, and part 3, rate at which the area of the water surface is increasing. Alright, so this is what we have. So now the keyword here is this semi-vertical angle right here. So semi-vertical angle simply means that one half of the angles of the cone is going to be equal to 45 degrees. That means that the total angle is actually going to be equal to 90 degrees, but half of it is 45 degrees. So that's what it means. So we're going to let the height of the cone be capital H, the depth of the water level be small h. We're going to let the radius of the cone be capital R, and let the radius of the water be small r. So sketch that, and this is what we have. So now as you can see, the semi-vertical angle is 45 degrees. So that's what they meant. Then the other half is also 45 degrees. So now we have capital H to represent the height of the cone, and then small h to represent the height of the water level at that point. So now we have dv dt, which was given as 30 cubic centimeters per second, and then the height h is 60 centimeters. Alright, so we're going to make use of the knowledge of trigonometry. So you can see that tan 45 shall actually be equal to r over small h, of which if I make r the subject, r shall be h tan 45. But remember, tan 45 is 1, so that means that r is equal to h centimeters. Now let's look at the volume of the water. So we know that the formula for the volume of the water is a third pi r squared h. So we're going to plug this. So where there is r, we're going to plug this h, and that's what we'll have. So you can say that will become h squared times this h will give me h cubed, and then we're going to differentiate that volume with respect to h, and I'll have dv dh being equal to pi h squared. But remember that h is 60 centimeters, so we're going to plug that in, and then we'll have dv dh being equal to 3600 pi. So now that we know that, we can now solve the first part. So you can find the rate of change of water level. So now by chain rule, dv dt is equal to dv dh times dh dt, because now we know there is a relationship between rate of change of water level and volume. So now, as you can see, dv dt was given as 30 cubic centimeters per second, and then dv dh is this 3600 pi. So make dh dt the subject, and it shall be 30 over 3600 pi, of which it will be 1 over 120 pi centimeters per second. So therefore, the rate at which the depth of the water level is increasing is 1 over 120 pi centimeters per second. Alright, so in part 2, we're being told to find the rate at which the radius of the water is increasing. Alright, so we're going to make use of the formula of volume, which is V is equal to a third pi r squared h. So in this case, we're going to differentiate with respect to r. So first of all, I want to eliminate this h right here. So remember that we said that r is equal to h. Actually, where there is h, we're going to represent it in terms of r, because r is equal to h. So we shall have it as V being equal to a third pi r cubed. So now if I differentiate this, I'll get dv dr being equal to pi r squared. But remember that r is equal to h, so that means that the value of r is also 60. So plug that in, and I'll have 60 times 60, of which dv dr shall be equal to 3600 pi. Now that I know that, I can find the rate of change of radius, of which now it shall be dr dt, which shall be now dr dv times dv dt, because there is a relationship between radius and change in volume in this case. So now plug that in, and remember that now we've seen that the r dv is actually the inverse form of this. So we're going to put this as 1 over 3600 pi, and then we had dv dt was given, and it was 30. So plug that in, and I'll have it as 1 over 120 centimeters per second. So therefore, the rate at which the radius of the water is increasing is 1 over 120 pi centimeters per second. Alright, so in part 3, we're being told to find the rate at which the area of the water surface is increasing. So when finding the surface area, this value of dr dt shall actually become useful, because there is a relationship between this radius and the rate of change of surface area. So area of water surface, we know it's going to be area being equal to pi r squared, and then we're going to have the a dr being equal to 2 pi r. So that's what happens when you actually differentiate that with respect to r. So now we remember that r is equal to h is equal to 60. So plug that in, and we'll have the a dr being equal to 120 pi. So now to find the rate of change of area, from chain rule, we're going to relate that to radius. So have it as dA dt. So we have the dA up and dt down, but relating it to the radius, so we have it over dr and then dr right there. So remember, we found that dr dt was 1 over 120 pi times this 120 pi. So we shall have it as 1 centimeters squared per second, and that is the answer. So therefore, the rate at which the area of the water surface is increasing is 1 centimeters squared per second, and that is the answer. Alright, so moving on to the next question. This is question number 14. So being told that water runs into a conical vessel fixed with its vertex downwards at a rate of 3 cubic centimeters per second, filling the vessel to a depth of 15 centimeters in a time of 1 minute. So being told to find the rate at which the depth of the vessel of water has been running for 7.5 seconds. So the difference in this question is we've added the concept of how much time it takes for water to run. So for example, we've been told that here that the vessel got full to a depth of 15 centimeters in a time of 1 minute. So that's the time it takes for the vessel to get full. So now remember, when the vessel is full, and we're saying that the water in it gets to a depth of 15 minutes, since it is full, it means that this 15 is also now the same as the height of the cone, because if water is full, if water is at the maximum, it also means that now at that level also, it's also at the same height with that of the cone. So that's very important to note in this question. So we're going to let the height of the cone be capital H, we're going to let the depth of the water level be small h, let the radius of the cone be capital R, and then we're going to let the radius of the water be small r. So in this question, we'll be given that the rate of we've been given that the rate of change of volume of water is 3 cubic centimeters. Then we're being told to find the dH dt, which is the rate of change of the depth of water. And then we've been told that the water fills the vessel to a height of 15 centimeters. So that means that also the height of the cone is capital H, which is 15 centimeters. So that's very important to note in this question. Alright, so now let's see this. And then we've been told that it takes 60 seconds for the cone to become full. So this is the cone. So now this, I've drawn it this way to just help us in measuring. Now we've been told that it took 1 minute to fill the vessel, but in the question we've been told to find the rate at which the depth of the vessel of water has been running for 7.5 seconds. So I want to know it before we go to 1 minute. So for that, let's first consider the level of water at some point as if before it got full, but we can label it this way. So as you can see, we've already identified that it means that therefore the height of the cone is 15 centimeters, and then small h is going to be representing the height of the water at any time. Alright, so now in this case we're going to consider different cases. So we're going to consider, for example, the case when the conical vessel is full. So that's going to be our first case. Now there is another formula of finding the volume of water that is there when the vessel is full. So we're going to first find the volume. So now, since we've been given the time it takes, and we know that the rate of change of volume is 3 cubic centimeters per second, we can find volume from, so total volume shall be equal to rate of change of volume times total time. So when the conical vessel is full, remember that it takes 1 minute to get full, and the rate of change of volume is 3 cubic centimeters per second. So we're going to have total volume being equal to this 3 times 60. So we're going to have it this way. So volume shall actually be equal to 180 cubic centimeters. So this is one way of finding the volume when it is full. But now remember that there is the other way. So we can actually also find the volume of the water when it is at the full, which is basically like the volume of the coin. So remember that we can also know that volume is equal to 1/3 pi r squared capital H. Now we have capital H because we are assuming that the water filled the entire vessel. So the height is going to be the capital H. So as we found before, we found that the volume of water is 180. So we're just going to equate that to this. And then we've seen that capital H, which is the height when the water is full, is the same as the height of the cone, which is 15. And then right now, the radius of the water surface when the cone is full is the same as the radius of the cone. So that's why we have it as capital R squared. Alright, so next I can cross multiply. So this 3 multiplies the 180 and I get 540. Alright, so divide both sides by 15 and I'll get 36 being equal to pi capital R squared. And then if I make capital R squared the subject, I'll have it as 36 over pi, of which the square root of that shall be 6 over root of pi. So now I know the radius of the cone, or the radius of the water surface when it is actually full. So next I need to find the radius of the water, the small r, at a point where the time that had passed was only 7.5 seconds. So that means I'm going to use this, I'm going to use the knowledge that I have here. Since I know capital R and I know capital H, I'm going to use that knowledge to find what r. So I'm going to use that to form an equation for small r. So now from similar triangles, I remember that I can say r over small h shall be equal to capital R over capital H, of which we know that capital R is going to be equal to 6 over root pi. So when I cross multiply it this way, I'll have small r being equal to 6h over 15 root pi. Alright, so now that I know the value of small r, I can now make a general formula for finding the volume of water at any height given. So now we know that the general formula can be V is equal to 1/3 pi r squared h, which h represents the height of water, this small h. So now I'm going to plug in this value of r, and this is what I'll have. So square that in and I'll have 36h squared over 225 pi, which if I multiply this h in, I'll have it as 36h cubed over 225 pi. Now you can see that when I multiply this to this, the pi values will cancel and I'll have 225 times 3, which will give me 675. So I have v being equal to 36h cubed over 675. So now I differentiate that and I have dvdh as being equal to 108h squared over 675. Now this shall be very useful in the final chain rule, so you just have to remember that. So but this is the formula for volume that we've actually now derived. So now we're going to be using the other method of finding the volume to find out what the volume was when we were at 7.5 seconds, and we're going to equate that to this. So now simplifying this further, it will give us 4h squared over 25. So now let's look at the volume of water after 7.5 seconds using the other method. So remember, the other method is total volume is equal to rate of change of volume times total time, which is the same as 3 times 7.5, which is 22.5 cubic centimeters. So now we know the volume of the water after 7.5 seconds. So we're going to equate it to this general volume so that it will help us find the height at the point where we have 7.5 seconds. So we're going to equate it to that and we'll get the value of h. So equate that and we'll have it this way, cross multiply, and that's what you get. Divide both sides by 36 and we'll have h cubed being equal to 421.875. So now when we multiply both sides by the power a third, we'll have h being equal to 7.5 centimeters. So therefore this is the height of the water after 7.5 seconds. So now that we know the height of water after that time, we can now find the rate of change of the water level. So now we're going to use chain rule to find it. So now remember, we're relating volume to height, so we're going to have it as dv dt being equal to dv dh times dh dt. Now we know that dv dh is this value right here times the dh dt that we're looking for. So dv dt is given as 3 being equal to this 4h squared over 25 times dh dt. So looking for the rate of change of the water level, so that means we're going to make this as a subject. So we're going to have dh dt being equal to 75 over h squared. But remember that h is 7.5 centimeters, just as we have there. So we're going to plug that in and this is what we'll have. So when we plug that in, we'll have 75 over 225, which is the same as a third centimeters per second. So that is the rate of change of water level. So therefore the rate of increase of water level is a third centimeters per second, and that is the answer they wanted. Alright, so our next question is a question from UNEB 2017, and this was question number 8. So being told that a container is in the form of an inverted right circular cone. Its height is 100 centimeters and its base is 40 centimeters. The container is full of water. So mark that we're being told that the container is full of water and has a small hole. So this is also another keyword. Now you should note, when a container has a small hole, it means that water leaks through it. So that means we're going to be losing water. So being told that water is flowing through the hole at a rate of 10 cubic centimeters per second. Find the rate at which the water level in the container is falling when the height of the water level in the container is halved. So that means we want to look at the point where h is a half of the original level. So now we've been given that the rate of water flowing out is 10 cubic centimeters per second. Now since water is leaking out, it means that now we have a negative value of the rate of change of volume. So now we're going to first let the height of the cone be capital H, let the depth of the water level be small h, let the radius of the cone be capital R, let the radius of the water be small r. Now you can already see that dv dt shall be equal to negative 10 cubic centimeters per second because water is flowing out, so the rate of change of volume is decreasing. And then we're being told to find the rate of change of water level. So that means we're looking for dh dt. And next we've been told that the height of the container is 100 centimeters and then its base radius is 40 centimeters. So we're going to plug that into our container. So this is our container right here. So as you can already see, the height of the container is 100 centimeters, its radius is 40 centimeters. So now r is going to be the radius of the water at any point, and then small h is also the height of the water at any point. So those are going to be very, very important for us. But first of all, we're going to form an equation to find the value of r. So you can see that if we can have, from the knowledge of similar triangles, r over small h is going to be equal to capital R, which is 40 over capital H, which is 40 over 100, of which if I make small r the subject, it shall be 40 over 100 H. Alright, so now if I simplify this, small r shall be equal to 2 over 5 H. So now that I know that, I can go to the next level. So I've been told that the volume of the water is halved. So we're looking for when the volume of water in the container is halved. So now we remember that V is a third pi r squared small h. So this is the general equation that we can use to find the volume of water at any point. So now we can have it as a third pi 2 over 5 h squared h. So now we can have it this way. So multiply that in, and we'll have these values here being squared. So I have 2 squared is 4, 5 squared is 25, and then this h will become squared. Alright, so next multiply 4 over 25 h cubed times this a third pi, and I'll have it as 4 over 75 pi h cubed. So the next step shall be to differentiate this, of which I'll have dv dh being equal to 4 over 25 pi h squared. But now remember that the value of h when the container is halved is actually going to be equal to a half of the container. So now remember that when the container is halved, I mean when we are halfway the container, it means that we're actually in the middle. So that means that now the height small h actually be equal to 50 centimeters. And why is that? It's because the original height was 100 centimeters. So since we're assuming that when the container was full, it means that the height of the water was 100 centimeters. So therefore, when it is halfway, the height of the container, the height of the water level in the container shall be 50 centimeters. So h shall be 50 centimeters. So plug that in and we'll have dv dh being equal to 4 over 25 pi times 50 squared. So I'll have 10,000 pi over 25, which when I divide 10,000 by 25, I'll have 400 pi. Now I can find the rate of change of the water level. So now we can have it as dv dt. So we know that the formula for dv dt shall be equal to dv dh times dh dt. But we know that the rate of change of volume is given. It's going to be negative 10. Then we found dv dh being equal to 400 pi. And then we want to find dh dt, which is the rate of change of water level. So make that the subject, and we'll have it as negative 10 over 400 pi, which shall give us negative 0.00796 centimeters per second, of which therefore the rate of rise of water level is negative 0.00796 centimeters per second. And why is the answer like this? It's because the water level is reducing, and that is the answer. Alright, so question 16, we're being told that a hemispherical bowl is being filled with water at a uniform rate. So when the height of water is h centimeters, we're being told that the volume is pi into bracket r h squared minus a third h cubed centimeters cubed. R being the radius of the sphere, mark that. Then find the rate at which the water level is rising when it is halfway to the top, given that r is 6 centimeters. So r is the radius of the bowl, and then the height of water is being represented by h. So we're going to let the depth of the water level be h as we've been given. And then we can say that r is 6 centimeters, and then we've been told that the bowl fills up in 60 seconds. So let's sketch the bowl right here. So this is what we have. So the radius of the bowl of the hemispherical bowl is actually 6 centimeters, and then we're going to have that arrow representing the radius of the water at any point, and then this is the height of the water. So h is going to be representing the height of the water at whatever point. So something you need to note about hemispherical bowl is it's actually half of a sphere. So a sphere is more basically round, so a hemispherical bowl is when we cut the sphere in half. Now something very important to know is the radius of the bowl can be measured this way, like this and like that, or in this direction like that. So now basically if water is to fill this bowl up, we can actually see, okay, let's see, we've cut it out like this. So if we've cut out half of it, this is what we have right there. So if water actually fills this hemispherical bowl, you can actually see that this height right here will actually be equal to this radius right here. So actually, so when the bowl is full, the value of h shall actually be equal to this 6 centimeters also. So that's actually the most important thing to note in this question. So if the bowl is full, the value of h is, small h is 6 centimeters. But if the bowl is not full, then the value of h will actually be a lesser value. Alright, so for this case, we've been told something clear, that if the bowl is being filled with water at a uniform rate, so that means that we're expecting the bowl to be full. Be told that that bowl fills in 1 minute, so that means that that's going to be helpful for us. So let's look at the case when that volume of water, when the bowl is full. Let's find the volume of water. So you can see that we've been given this formula right here. Now, as I've said, that when the bowl is full, it means that h shall actually be equal to 6 centimeters, because the water level shall actually fill it completely. So h shall actually be equal to 6 centimeters when the bowl is full right there. And then the value of r of course remains the same because r represents the radius of the bowl. So we're going to substitute the values in. So where there is h, we've put 6 and 6 right there, and then r is definitely 6. Alright, so I'm going to get v being equal to pi times bracket 216 minus 216 over 3. So 216 divided by 3 will give me 72. So now 216 minus 72 will actually be 144 pi cubic centimeters. So this is actually the volume of the water when the bowl is full. So now there are two ways of finding the volume of the water when the bowl is full. So there is another formula. So alternatively, volume of water when the bowl is full can also be found using the formula total volume is equal to rate of change of volume times total time. So why are we using this? We've been given the total time that it takes for the bowl to get full, and that was 1 minute. And then we've also known that the volume of water when the bowl is full is going to be equal to this value right here. So that means we're going to use this to find the rate of change of volume, which was actually not given to us. So we're going to substitute that in. So we have 144 pi being equal to dv dt times 60. So if I make dv dt the subject, it shall be 144 pi divided by 60, or which dv dt, which is rate of change of volume, shall actually be equal to 12 over 5 pi cubic centimeters per second. So now that I know the value of dv dt, I can now work out the rate of change of water at any point. Alright, so as I've stated before, when the bowl is not full, the value of r is actually not equal to the value of h, because the value of h should actually be equal to less than r. So now we're going to have r, of course, definitely remaining as 6, and we're going to use the general formula of the volume given, and then we're going to differentiate it. So this is what we have right here. So we need to find the value of dv dh, and that's going to be very important as we work out the next step. So I'm going to plug in the value of r, and then I'm going to have 6h squared minus a third h cubed. So next I'm going to differentiate the values within, and then I'll have dv dh being equal to pi into 12h minus h squared. So now that I know the value of dv dh, I can now find when the bowl is halfway full. So when the bowl is halfway full, halfway of course means that h shall actually be equal to half of the radius. So h shall actually be equal to 3 centimeters. So I'm going to plug that inside right here. Then I'm going to have dv dh being equal to this. So I have pi into 36 minus 9, which shall actually give me 27 pi. So now I know the value of dv dh. So now that I know that, I can now find the rate of change of the water level, which is dv dt being equal to dv dh times dh dt. So plug in the values of dv dt, which is 12 over 5 pi being equal to dv dh, which is 27 pi times dh dt. So make dh dt the subject, which actually be equal to 12 pi over 5 times 27 pi, of which the answer shall actually be equal to 4 over 45 centimeters per second. So therefore the rate of rise of water level as it is halfway to the top is 4 over 45 pi centimeters per second, and that is the answer. Alright, so the next question is the question from UNEB 1999, and this was question number 15. So being told that a hemispherical bowl of radius a is initially full of water. The water runs out through a small hole at the bottom of the bowl at a constant rate, such that it empties the bowl in 24 seconds. Given that when the depth of water is x centimeters and the volume of water is a third pi x into bracket 3m minus x centimeters cubed. So we've been given the volume of water. Show that the depth of water at that instant is decreasing at a rate of this. So that means that we know what this value here. So we've been told to find how long it will take for the depth of the water to be a third a centimeters and the rate at which the depth is decreasing at that instant. So we've been given a lot of things, and that's going to be very, very important. So being told, given that when the depth of the water is x, so remember that instead of h like the others, the depth of the water shall actually be equal to x. So let me first show you something. So being told to show that the depth of the water at that instant is decreasing at a rate of that. So that means that we expect the value of dx dt. So we have proved that dx dt should actually be equal to a cubed, because dx represents the height of the water, into 36x and into bracket 2a minus x. So that's going to be very important. So that's what we're going to be looking for. Then we've been told that given that when the depth of the water is x centimeters and the volume of water is this. So we've been given the general formula for the volume of water. So this is going to be very, very helpful. So let's first sketch this. So we've seen that it takes 24 seconds for the bowl to empty. So remember that in this case, water is running out of the bowl. So that actually means that the value of dV dt, which is rate of change of volume, should actually be a negative, because water is actually running out of the bowl because of the small hole at the bottom. So it takes 24 seconds for the bowl to empty. So this is the bowl that we actually have. So now we've seen that its radius should actually be equal to 8 centimeters, and then we're going to have that small r representing the radius of the water surface at any point. Then x is going to represent the height of the water at any point. Alright, so let's look at the first case of when the bowl is full. So as I've said before, when the bowl is full, the value of x should actually be equal to the value of the radius, because this is actually half of a sphere. So this value here, when the water level is full, should actually be equal to that. So x should actually be equal to 8 centimeters. So remember, we've been given the formula for volume as this value that we have right here. So that means that wherever there is a, we're going to plug in an x. So we're going to have it this way. So now where there is this x, we're going to place in an a. So we're going to have it as that. So now when we work this out, we'll have 3a minus a, which is 2a. So we're going to multiply that, and we'll have, so we're going to have v being equal to 2 over 3 pi a cubed. Now the reason we maintained and focused on a was because a is representing the radius of the water level when it is actually full. So now alternatively, volume of water when the bowl is full can also be found using the formula total volume being equal to rate of change of volume times total time. So as you can see, we know the total time, and now we've actually known the total volume, which is going to be represented by this formula. So you can find the rate of change of volume. So we're going to have 2 over 3 pi a cubed being equal to dv dt times 24. So now if I make dv dt the subject, I shall have it as 2 pi a cubed over 3 times 24, of which I'll have it as 2 pi a cubed over 72, which when simplified further will be pi a cubed over 36 centimeters cubed per second. So now I know the rate of change of volume in this case. Alright, so next I'm going to consider the case when the bowl is not full. So we know that when the bowl is not full, x should actually not be equal to a, because the value of x should actually be equal to less than a. So I'm going to use the general formula of volume that I was given, that v is equal to a third pi x squared times 3a minus x. So I'm going to multiply this x squared inside, and this is what I have. And then I'm going to differentiate with respect to x, and then find dv dx being equal to a third. Now the reason we're finding it to dv dx is because now this should actually help me and take me closer to finding the rate of change of the water level, of which at the end I know I'm looking to find that dv dt is equal to dv dx, because dx now represents the height of water, times dx over dt. So this actually takes me a step closer. So now I'm going to find the dv dx being equal to 6ax minus 3x squared. So now that I have that, I can now find the rate of change of the water level from chain rule. So by chain rule, we can say that dv dt should actually be equal to dv dx times dx dt. Alright, so plugging the values in, I can say that dv dt is this value right here. Then dv dx, we've just found it right now. Then times dx dt. So now plug those in, and then makes dx dt the subject. So dx dt should actually be equal to pi a cubed over 12 pi times bracket 6ax minus 3x squared. So next I can see that the pi values cancel, so I remain with that. Alright, so next step, I can set, I can actually factorize out 3x from here. So now multiply 3x times 12, I'll have to have 36x, and into bracket I'll have 2a minus x. Alright, so next I can set, I can actually take this value here to the top, which will give me 36x into bracket 2ax minus x, all of this into the power negative 1. And this is the proof that they wanted. So this is how we showed the depth of the water. It was decreasing at this rate at that instant. So this is the proof. Alright, so next we're being told to find how long it will take for the depth of the water to be a third a centimeters and the rate at which the depth is decreasing at that instant. So now we've been told the value of the depth that they want, the value of x should actually be equal to a third a centimeters. So that means we're going to first find that volume by plugging it into this general formula. Alright, so volume when the depth of water is x is equal to a third a centimeters, we're going to get it by plugging in into the general formula that we have right here. So where there is x, we're going to plug in that height of water level, then this is what we have. So when I multiply the third, when I square this, I'll have s squared over 9, and then here I'll have it that way. So now when I work this out, here I'll have 9a minus a over 3, then this shall be that. So 9a minus a is 8a, so I have it this way. So now open those brackets and multiply, and I'll have 8a cubed at the top over 81 pi. So now this is the volume of the water when the depth is x is equal to a third a centimeters. Alright, so now that I know the depth of the water level when we have it as x being equal to that, now next I need to know the amount of water that was lost before we had it at this level, because the water level is decreasing. So I need to know the amount of the volume of water that was lost. So what happens is I need to get the volume when full minus this volume right here. So once I have that, I'll now use a formula to actually find how much time it takes to lose that water that actually was lost. So now volume of water emptied or volume of water lost at this point shall be equal to volume when full, which is 2 over 3 pi a cubed minus this volume that was remaining at this time. So now I have v being equal to 46a cubed pi over 81. So now this was the volume of water that was lost. So now that I know that, I can now use this alternative method for volume to find time it took to lose this volume of water. So remember, total volume is equal to rate of change of volume times total time. So plug that in. I know that the rate of change of volume, we've actually already found it, and I know the total volume at this point, total volume of water that was lost. So plug that in. I'll have it as 46a cubed over 81, then multiply it with pi, and then dvdt, we know it, dvdt is actually pi a cubed over 36, then times t. So now I want to find the time it took to lose that amount of water. So now cross multiply this, and I'll make t the subject and t shall be equal to that. So this pi and the a cubed cancel, and I'll be left with 1656 over 81. So when I solve that, I have time being equal to 20.44 seconds, of which therefore I can now say that it takes 20.44 seconds for the depth of water to be a third a centimeters, and that is the answer they wanted. Alright, so next we're being told to find the rate at which the depth is decreasing at that instant. So that means at the instant when the depth of the water was a third a centimeters. But now remember that at first we were being told to show the depth of water was decreasing at a rate of that. So that means we know the value of dx dt, so we're going to be making use of that. So we had proved that when the depth was x centimeters, this was the formula, dx dt was actually equal to a cubed into 36x times 2a minus x to the power negative 1. So this was when the depth was that. So that means that when the depth of the water is x being equal to a third a centimeters, you can actually substitute this for where we have x into that formula. So this is what I'm actually going to have. So I can actually now find the volume of the water that was decreasing at that instant. So this is what I'll have right now when x is a third a centimeters. So plug that in and solve it, and this is what I have. So here I'll have 6a minus a, which is 5a, and then this is what I'll have right now. So multiply those values. Actually this 3 and this reduce, and I have 4a right here. So I have a cubed times that. So now this is what I have. So now 4a times 5a is 20a squared, of which I can take that down, and it shall be a cubed times 1 over 20a squared. So now when I multiply this, I'll be left with a over 20 centimeters per second. So therefore the depth is decreasing at a rate of a over 20 centimeters per second when the depth is a third a centimeters, and that is the answer they wanted. Alright, so moving on to question number 18. We're being told that a horse trough has a triangular cross-section area of height 25 centimeters and base 30 centimeters and length 2 meters. A horse drinking steadily and when the water is, so a horse is drinking steadily, and when the water level is 5 centimeters below the top, it is being lowered at a rate of 1 centimeters per minute. Find the rate of consumption in liters per second. So we're going to let the height of the water level be small h, let the height of the trough be capital H, let the length of the trough be L, and then we're going to let the base of the trough be B. So we've been told that it has a triangular cross-sectional area. So that means we're going to sketch it. So we can say the length of it is 200 centimeters, the height of it is 25 centimeters, and then the base of it is 30 centimeters. And then we've been told that the rate of consumption is 1 centimeters per minute. So that means that the h, the t, the height of which the water level is lowering, so the rate at which it's lowering is actually 1 centimeters per minute. So this is what we have. So you're sketching the horse trough here, and then this is it with a triangular cross-sectional area. So let's label it. So we're going to divide this like that. So this is a rectangle, and then we can see that the base is 30 centimeters. Then we can have here, so a small h shall represent the height of the water at any point, and then we can see that this 25 centimeters is actually the general height of the trough, and then the length is 200 centimeters. So if the bowl is, if the trough is full, it actually means that h is equal to 25, but now h is representing the height of the water at any point. Alright, so according to the question, we've been told that the horse was drinking steadily, and when the water level is 5 centimeters below the top. So that means that we've already been told the height of the water level. So that means we know the value of h. So we've been told it's 5 centimeters from the top. So what that means is h is actually 25 minus 5, so h shall be equal to 20 centimeters. So we know the value of h. Alright, so the next step is we want to know the base of the water level right here. So we need to know this value right here, and we're going to use the knowledge of similar triangles to find this value right here. So as you can see, from similar triangles, to find the base of the water surface, we're going to have b over small h, of which this b will represent the base of the water, and then this h is actually the height of the water level, shall actually be equal to 30, of which 30 is actually the base of the trough, and then 25 is the height of the trough. So this is actually going to be what we use. And then if we make the base of the water surface a subject, so the base of the water surface actually be equal to 6 over 5 h. Now this is almost similar to what we've been doing before, where we've been letting r to actually be equal to something in terms of h. So now instead of r, the base of a trough is actually what is the radius, like the way we actually look at the cone and the rest. So right now we deal with the base. Now to find the volume of water in the trough, we know that the volume is actually a half times base times height times length. So we're going to have v being equal to a half times, so where there is base, we're going to put 6 over 5h, so that's why we have it there. And then remember that length is 200, so this is what we have, and then we have h right there. So now if we multiply these, we'll have 6 over 5 times a half is 6 over 10h, so multiply this together and we'll have 120h squared. So now next we can actually differentiate that to find dvdh. So dvdh actually be equal to 240h, but h, remember, is 20 centimeters, so that is the height of the water. So plug that in and we shall have 4800. Alright, so now that we know that the value of dvdh is 4800, we can now find the rate of consumption of water, which is the value of dv dt. So by chain rule, dv dt shall actually be equal to dvdh times dh dt. So dv dt shall actually be equal to 4800 times 1, which will have dv dt being equal to 4800 cubic centimeters per minute. But we've been told that we want this in liters per minute, so we're going to convert it to that, and we do that by dividing 4800 by 1000. So we shall have dv dt being equal to 4.8 liters per minute. So therefore the rate of consumption is 4.8 liters per minute, and that is the answer they wanted. Alright, so question number 19, we're being told that a ladder 5 meters long is leaning against a wall. The foot of the ladder is pulled along the ground away from the wall at a rate of 2 meters per second. How fast is its height on the wall decreasing when the foot of the ladder is 4 meters away from the wall? So let's solve this. So first of all, we're going to let the height of the ladder on the wall be y, and we're going to let the distance of the ladder from the wall be x. And we're going to let the length of the ladder, which is also very important, to be L, and that was given. So as you can see, we're dealing with this. So now we're saying, let's look at this critically. We're being told that the foot of the ladder is pulled away from the wall. So that means we're looking at this value of x at a rate of that. So that means that if we're representing the distance from the foot of the ladder as x, that means we have dx dt being equal to this 2 meters per second. How fast is its height on the wall decreasing when the foot of the ladder is 4 meters away from the wall? So that means that we're looking for dy dt. So that's actually what we're looking for. As you can see, dy dt in relationship to dx dt. So let's form the chain rule for this. So I'll have dy at the top, and then we're going to have dt at the bottom. So we're relating the dy to the change of the distance of the ladder from the wall. So that means that we're relating it to x. So comparing it to x, so we're going to have x right there. So this is the formula that we're looking for. So we have to find, so we know what dx dt is. So that means we're going to look for dy dx, and that's going to be the important thing. Alright, so dy dt is actually what we need, but we're going to first find dy dx before we actually find it. Alright, so here is the sketch of the ladder, and we've been told that it's 5 meters long. And then we've been told that the foot of the ladder is 4 meters away from the wall. So that means that we have it as 4 meters. And y is the height of the wall. Actually, it's height of the ladder as it's decreasing. So this is the height right here. So now we need to first find the value of y. Alright, so from Pythagoras theorem, we can see that y squared plus x squared should actually be equal to L squared. So plug those in, and this is what you have. So L squared is 5, L is 5, so we'll have it as 5 squared. So I have y squared plus x squared being equal to 25. So this shall be my equation 1. So from equation 1, I can see that I can plug in the value of the distance from the ladder, which is the value of x. So I have y squared plus 4 squared being equal to 25. Now the reason I made it equation 1 is because I'll be making use of it again to find the value of dy dx. So now I have it this way. So I have to first find the value of y. So y squared should actually be equal to 25 minus 16, which y is root of 9, of which the answer is 3 meters. So now I know the value of y. So now that I know the value of y, I can now go back into equation 1 and use it to find the value of dy dx. So y squared plus x squared is equal to 25. So if we differentiate this, I'll have 2y dy dx plus 2x being equal to 0. So now we remember that y is 3 and x is 4. So plug those in, and I'll have 2 times 3 dy dx plus 2 times 4. So I'll have 6 dy dx plus 8 being equal to 0. Alright, so now we have to make dy dx a subject. So dy dx should actually be equal to negative 8 over 6, of which I'll have dy dx being equal to negative 4 over 3. So now I know the value of dy dx. So now I can use the chain rule formula that I actually stated before. So now we can set by chain rule dy dt should actually be equal to dy dx times dx dt. So plug in those values, and I'll have it as negative 4 over 3 times 2, of which the answer shall be negative 8 over 3 meters per second. So therefore, the height on the wall of the ladder is decreasing at a rate of negative 8 over 3 meters per second. So actually the value is negative in the answer because the height is decreasing. Alright, so lastly, I have an exercise for you. These are numbers I encourage you to try out to get better at rates of change. So I did so much research, and I made sure to give you answers, as you can see right here. So these answers in brown are answers you can compare to what you get to make sure that you're actually on the right track. So try these out. Alright, so the questions continue. I have question 6, 7, and these are its answers. Question 8, question 9 with its answers. So I still encourage you to pause and copy the questions before you try them out. And then I have question number 10 right here, and these are its answers. And then lastly, I have question number 11. So try these out and perfect your knowledge of rates of change. I hope this video was helpful. Thank you for watching. Thank you so much for watching this video. I hope the video really helped you. If it did, feel free to share the video with all your friends and help as many as you can. And then if you really like the video, feel free to give the video a like or a thumbs up, and then tell me in the comments if the video really helped you, and I'll try to get time and reply to your comments. And then if you're new to this channel, I encourage you to join the community by subscribing, and then make sure to hit the notification bell so that you get updated every single time I upload a new video. Thank you so much for watching, and I'll see you in my next video.